So it is really cold outside right now. I'm from Arizona. I'm not used to this cold weather. So why do we have cold winters in the first place? Every year that I ask students this, the most common response is, well, right now it's winter, so we're farther away from the sun. And in the summer, we're closer to the sun. But that doesn't totally make sense, because in New Zealand right now, it's summer. Part of it has to do with the daylight. So right now the sun is rising, and on Christmas Day here in Germany, that sun is going to stay up for about 8 hours and 24 minutes. In the summer, in the middle of June, however, the sun is going to be up for about 16 hours. So that's almost twice as long as a winter day. So our area just spends more time bathing in the sun in the summer as opposed to in the winter. But that doesn't fully explain why we're experiencing winter, because in Antarctica right now, it is really cold. It's about negative 38 degrees Celsius right now in Antarctica. But they have a 24-hour day. The sun does not set today in Antarctica. So why isn't it super hot in Antarctica right now? So daylight is not the only thing that explains the seasons. If we want to understand this further, we have to consider the tilt of the Earth. Let's imagine that this lamp is the sun, and here we have the Earth as it rotates. Okay, you'll notice that it is rotated on an axis. So right now this is winter for Germany, and the Earth is actually tilted away, the northern hemisphere is tilted away from the sun. So why is Europe experiencing shorter days than Africa? Let's consider these points along this prime meridian longitude on the Earth. Notice how when the Earth rotates, okay, we've got England right here is in daylight still. We've got Ghana is still in the daylight, and here in the Atlantic Ocean, it's still experiencing daylight. As we turn the globe, notice how Europe enters the night before Ghana, okay? And even as the northern hemisphere is in the night, we see the southern hemisphere still is experiencing more daylight, okay? So it is going to be bathed in the sun for a longer period of time. Now, back to the Antarctica question. Notice how as the Earth is rotating, the south axis is pointed towards the sun, and so therefore Antarctica is being constantly bathed in 24-hour light. The northern axis, however, is facing away from the sun in winter, and so the North Pole is not experiencing any sunlight. So again, if Antarctica is in the sun for 24 hours, how come it's still cold? Well, temperature also has to do with the fact that the Earth is a sphere. I'm going to use this laser thermometer to measure the temperature of the Earth's surface in the light. Notice how when I point at the equator, I'm at about 60.7 degrees Fahrenheit. The farther I move up from the equator, notice how my temperature decreases. The farther you get away from the equator, the less direct light there is, and so the colder it gets. So even though Antarctica is being bathed in sunlight, that light is so indirect that it's still cold. Let's look at how the Earth experiences daylight at different points in the year as it orbits the sun. To do that, we're going to take it out to the gymnasium, and we're going to use a laser. All right, see that laser point? We're going to use this laser to represent a ray of sunlight. Notice how this beam of sunlight looks like a single point from the sun's perspective. as we approach the Earth and look at how that sunlight beam reaches it, you'll notice that it is stretched out, okay? It's still that single point, but that amount of sunlight is being stretched over a larger area. That's what it means for this light to be indirect, okay? It's just glancing off of the surface of the Earth. So what happens if I take this laser and put it completely parallel to the floor and then map out the Earth's course around this sun, with this laser just representing a single beam of sunlight perfectly perpendicular to the Earth's surface? Okay, so this Earth is positioned to what it would be approximately on Christmas Day. The northern hemisphere is facing away from the sun, and the southern hemisphere is facing towards the sun. And where does that beam of sunlight show up? That beam of sunlight is perfectly perpendicular to this dashed line, which we call the Tropic of Capricorn. This is what's known as the December solstice, and anyone right below that perfectly perpendicular ray of sunlight is not going to be experiencing any shadow. Okay, the sun will be directly above them at high noon. So why is it called the Tropic of Capricorn? Capricorn is Latin for goat horn. How are you? Are you good? Yeah? Yeah? Don't charge at me, okay? The reason is because when they named this line, right behind the sun was a constellation called Capricorn. Let's move the Earth as it would orbit around the sun from December to March. So that was December, and as we orbit around the sun, the axis is still going to be pointed the same direction. So that same beam of sunlight that is perpendicular to the Earth's surface is going to appear right here along the equator. This is what we call the March equinox. The sun is directly overhead the equator, and this is when the Earth is going to be experiencing equal night and equal day. So just remember, the March equinox, equal day and equal night, happens when the sun is lying over the equator, which is also why Ecuador is called Ecuador. And so each side of the Earth here is going to be experiencing an equal amount of day and night, because the tilt is not tilted away or towards the sun, it's tilted towards the side. So why are there a bunch of tropical rainforests right here at the equator? It all has to do with the sun. That direct amount of sunlight is going to cause the air temperature to warm up, and that warm air is going to rise. As that warm air rises above the surface of the Earth, it's going to start cooling, at which point it's going to start condensing, and that's going to condense as rain. That rain's going to fall and provide a lot of water for these rainforests here at the equator. Now, as we move from the equator and the tropic zones and move more north or south, we get to the subtropical zones, where we have a lot of the world's deserts, okay? That's because the cold air that's risen from here has lost all of its water at the rainforest, and it starts to move towards the northerly or southerly latitudes, and it descends as dry air. So we get these dry deserts because all the water has already been lost at the equator. So what happens in June? The Earth's orbit is going to continue its journey around the sun with the axis still pointed this direction. In June, the Earth is going to be the opposite position as December. So here's my sunbeam, all right, and we've moved the Earth from March to June. And where does the sunbeam lie perfectly perpendicular to? The Tropic of Cancer. So this is what summer in Germany is like in June. The North Pole is facing directly towards the sun, okay? And because of that, the sun is not shining directly and perfectly above the Tropic of Capricorn. Instead, it's right above the Tropic of Cancer. This is what the June solstice is, okay? It's called solstice because the sun stands still. Sol, sun, stis is still, okay? So notice how when we looked at December, okay, the sun stood still there above the Tropic of Capricorn. And then we get March, and then the sun shines directly above the Tropic of Cancer, and it stands still. And then it comes back here, and then solstice. Okay, solstice, equal days, solstice, all right? So for us, this is our longest day. People who are along this direct line will experience no shadow. So that's 0 shadow day for them in June along the Tropic of Cancer. So wherever in the year it's shining directly over, at high noon, those people are not going to experience any shadows, okay? So that's what the Tropic of Cancer is. So again, why do we call it the Tropic of Cancer? Cancer is Latin for crab, and it's based off of a constellation, again. When they named this tropic, or this line, the constellation that looks like a crab was behind the sun. Okay, so as the sun is directly shining over this northern hemisphere and providing it with a lot of sunlight, what's going to happen to the carbon dioxide levels in the atmosphere of the Earth? Well, all of that sun is going to drive photosynthesis. And so all of these forests that are up here, and all of the trees and even the algae in the ocean that are experiencing that direct sunlight, okay, are going to start doing photosynthesis, which means they're going to start drawing in that carbon, and they're going to start sequestering that carbon dioxide. And so what we'll see here as the sun lines up over the Tropic of Cancer is we will see a dramatic drop in the amount of carbon dioxide in the atmosphere, okay, as all that sun drives that process that allows that carbon sequestration to take place. Remember, this is the Keeling curve. This is when we take that dip in the Keeling curve. The northern hemisphere influences the carbon dioxide the most because the northern hemisphere has more land than the southern hemisphere. All right, it's June. The Earth is going to continue its orbit with the axis facing the same direction, and we're now going to enter September and enter the September equinox. All right, at this point, the Earth is not facing away or towards the sun now that we are in September. Because it's not facing away or towards the sun, we're going to experience equal day and night. And where does the sun line directly above in September? Right above the equator. Remember, equator, equinox, okay? And then, once again, the Earth is going to continue its orbit around the sun, still facing the same direction. And now we've reached December once again, with the northern hemisphere facing away from that beam of sunlight, that sun that is shining on us. So now, northern hemisphere would be experiencing winter, but because the northern hemisphere is facing away from the sun, the southern hemisphere is facing towards the sun. And so they are going to be experiencing, again, even though indirect light down here, they're still going to be experiencing 24 hours of daylight, as opposed to northern hemisphere, which will experience 24 hours of darkness. And so right now it's colder outside because we're positioned right there in the orbit. So it's the Earth's orbit, the Earth's tilt, and the spherical shape of the Earth that all determine temperature differences, light intensity, and why we experience seasons. But couldn't the seasons still be caused by distance from the sun? Not really, because when the northern hemisphere is experiencing winter, it's actually closer to the sun than when the northern hemisphere is experiencing summer. In July, we are 152 million kilometers away from the sun. But in January, we're actually 5 million kilometers closer to the sun than that. All right, hopefully that explains the miracle of seasons to you. Now, go do your homework.